The universe has a simple rule that changes everything. Light takes time to travel. This means distance is not only a measurement of space, it is also a measurement of time. The farther away an object is, the older the light is when it reaches Earth. In astronomy, looking outward is also looking backward. In this episode, the focus is on an instrument built specifically to look back, farther than any telescope before it could easily see, and with a clarity that reshapes questions about the early universe. That instrument is the James Webb Space Telescope, often shortened to JWST. The significance of JWST is sometimes reduced to a single idea: it takes beautiful pictures. That is true, but the deeper story is more interesting. Webb is a telescope designed to reveal what was previously hidden. It is built to detect light that has been stretched by cosmic expansion. It is built to see through dust. It is built to study the earliest galaxies, the birth of stars, and the chemistry of distant worlds. In this episode, the goal is to understand why JWST changed the conversation so quickly, what kinds of discoveries it makes possible, and why its first results created both excitement and tension within cosmology. Welcome back to Beyond Space, where we explore the universe one mind-blowing idea at a time. To understand why JWST is different, it helps to start with a practical question. What kind of light is it designed to see? The human eye is tuned to visible light, a narrow portion of the electromagnetic spectrum. But the universe does not limit itself to what humans evolved to perceive. Many of the most important cosmic processes are best observed outside the visible band. JWST is primarily an infrared telescope. Infrared light has longer wavelengths than visible light. There are two key reasons why this matters. First, cosmic redshift. The universe is expanding. As space expands, light traveling through it gets stretched. Wavelengths become longer. Light emitted in the ultraviolet or visible band billions of years ago may arrive at Earth shifted into the infrared. This is not a small effect. At large distances, meaning at early cosmic times, redshift can move the light of young galaxies out of the visible range entirely. Second, dust. Dust is common in space. It is made of tiny particles, carbon-rich grains, silicates, and other materials, spread through interstellar and intergalactic environments. Dust absorbs and scatters visible light, making many regions opaque in visible wavelengths. But infrared light can pass through dust more effectively. This means a telescope optimized for infrared can see into star-forming regions, peer into dusty galaxies, and reveal structures that visible light telescopes can only partially observe. In this episode, these two concepts, redshift and dust, form the foundation of why Webb exists. There is also a third major reason: temperature. Infrared detectors are sensitive to heat. A warm telescope can contaminate its own observations by emitting infrared radiation. To see faint infrared signals from the distant universe, the telescope itself must remain extremely cold. JWST's design reflects this requirement. Its instruments are protected by a large sunshield that blocks heat from the Sun, Earth, and Moon. The telescope operates far from Earth, near a stable gravitational environment known as the second Lagrange point, or L2. At L2, Webb can maintain a stable orientation with the sunshield facing the Sun, keeping the telescope's instruments cold enough to detect faint infrared light. So JWST is not simply a large telescope in space. It is a carefully engineered system designed to hold a cold, stable observing platform in a location where infrared observations are practical. With this understanding, the next question becomes, what is JWST actually looking at? One of Webb's central missions is to observe the early universe, galaxies that formed not long after the first stars began to shine. This is often described as looking back toward the first galaxies, but the phrase hides complexity. The early universe was not a single moment. It was an evolving sequence of eras, defined by changes in matter, radiation, and structure formation. There is the era after the cosmic microwave background, when the universe cooled enough for atoms to form. There is the period when the first stars ignited. There is the era when early galaxies assembled from smaller pieces. There is the epoch of reionization, when ultraviolet radiation from early stars and galaxies ionized much of the intergalactic medium. These eras are not fully understood in detail because the early universe is hard to observe directly. It is faint, it is distant, it is redshifted, and it is often obscured by dust and by the simple fact that the earliest objects were smaller and less luminous than later galaxies. Webb was built to push into this region with more sensitivity and resolution. In this episode, one of the most striking early results is the deep field imagery. A deep field is a long exposure of a small patch of sky, revealing objects too faint to see in shorter observations. Webb's deep fields showed something that many viewers immediately felt, even without technical background. The sky was crowded with galaxies. This crowding was not entirely unexpected. Hubble deep fields had already revealed thousands of galaxies in small patches of sky. But Webb's view was different in character. It revealed faint galaxies with sharper structure. It revealed color and morphology in ways that made distant objects feel more present. And it raised a scientific tension that became widely discussed. Some early galaxies appeared surprisingly bright and seemingly well-formed for their age. This does not mean Webb proved that cosmology is wrong. It means Webb introduced data that required careful interpretation. There are multiple reasons why an early galaxy might look brighter or more massive than expected. It might be forming stars at an unexpectedly high rate. It might contain less dust than assumed, making it appear brighter. It might be magnified by gravitational lensing from matter along the line of sight. Its mass might be overestimated due to uncertainties in modeling starlight, dust, and star formation histories. The relationship between observed brightness and intrinsic mass in the early universe might be more complex than simplified assumptions. In this episode, the important point is that early Webb results did not deliver a single clear narrative. They delivered a more realistic one. The early universe is complicated, and when a telescope becomes powerful enough, it reveals not just answers, but deeper questions. A new instrument often works this way. It doesn't simply confirm what is known. It exposes where the models are weak. This is not a failure of science, it is progress. In addition to early galaxies, Webb has another capability that reshapes public imagination: the study of exoplanet atmospheres. Exoplanets are planets orbiting stars beyond the Sun. Thousands have been discovered, many through indirect methods such as transits, small dips in brightness when a planet passes in front of its star. JWST can do more than detect transits. It can analyze how starlight passes through the thin ring of a planet's atmosphere during a transit. As light filters through an atmosphere, molecules absorb specific wavelengths. This creates spectral features, patterns that can be measured. In this episode, it is important to state what this means and what it does not mean. It does not mean Webb can see alien cities or detect life directly. Webb's atmosphere measurements are subtle and require careful statistical analysis. But it does mean something remarkable. Humanity can measure the chemistry of a world orbiting another star. That fact alone represents a profound change in the relationship between Earth and the cosmos. For most of history, planets were visible as points of light, with no way to know what they were made of. Even within the solar system, understanding planetary atmospheres required spacecraft visits. Now, the spectral fingerprints of atmospheres can be measured across interstellar distances. This opens a long-term path towards searching for biosignatures, chemical combinations that might suggest biological activity. But the key word is path. The search for life is not a single detection. It is a gradual refinement of measurements, models, and understanding of planetary environments. In this episode, Webb's exoplanet capability serves as another example of how improved perception changes the questions. Instead of asking only, "Are there planets out there?" the questions become, "What are they like? What are their atmospheres made of? How do they evolve? Which ones might be stable enough to host long-term chemistry?" This also connects to a broader theme of the season. Signals and light are carriers of information. In episode 2, radio signals were discussed as natural phenomena that can be verified, interpreted, and used. In this episode, ancient light and atmospheric spectra serve a similar role. The universe is not being interpreted through direct touch. It is being interpreted through patterns in electromagnetic radiation. In addition to distant galaxies and exoplanets, Webb also looks closer to home. It studies the formation of stars within dusty clouds. It observes planetary systems in the making. It reveals details in nebulae, structures shaped by radiation, winds, and gravity. These observations help connect cosmic history to local processes. The formation of stars and planets is not separate from the story of the universe. It is a continuation. The same physics, gravity, radiation, chemistry, scales across vast distances and times. In this episode, Webb's ability to see through dust is central. In visible light, a star-forming region can appear like a glowing nebula with dark lanes. The dark lanes are dust, material dense enough to block light. In infrared, some of that dust becomes transparent, revealing embedded stars and structures that were hidden. This changes the understanding of how stars form, the distribution of mass, the fragmentation of clouds, the birth of protostars, the influence of outflows and jets. The same principle applies to galaxies. Dust can hide star formation. Infrared can reveal it. So Webb is, in many ways, a telescope that reveals the hidden scaffolding of the cosmos. Now, the question becomes, why does any of this lead toward mystery? Because clarity can be unsettling. When observations become more precise, they can expose disagreement between expectation and reality. That disagreement is not necessarily a contradiction. It is often a sign that the simplified version of a model needs refinement. In this episode, one of the major scientific discussions Webb intensified involves the early growth of structure. How quickly did galaxies assemble? How quickly did they form stars? How quickly did black holes grow? How did gas cool and collapse in the presence of early radiation fields? These questions are technical, but the underlying idea can be expressed simply. Webb is showing that the early universe may have been more active and more structured earlier than previously assumed. This is not the same as saying the Big Bang model is wrong. It is not the same as saying everything must be rewritten. It is saying that the early universe, once beyond clear observation, is now being measured. And measurement tends to replace simple stories with complex ones. A related and particularly compelling question involves supermassive black holes. Many galaxies, including the Milky Way, host supermassive black holes at their centers. These black holes can have masses millions or billions of times greater than the Sun. In the modern universe, supermassive black holes are common in large galaxies. But in the early universe, the existence of very massive black holes at surprisingly early times raises the question, how did they grow so quickly? Black holes grow by accreting matter. They can also grow through mergers. But there are limits to how quickly a black hole can grow through standard accretion processes, because intense radiation from the infalling material can push against additional inflow. If very massive black holes are present early, it implies either the initial black hole seeds were larger than expected, accretion occurred more efficiently than simplified models allow, mergers happened rapidly, or some combination of these. JWST is not the only tool for studying early black holes, but its ability to detect faint high redshift objects supports broader investigations into early galaxy and black hole evolution. In this episode, this becomes a bridge toward the season's final destination. The season has been moving through layers of perception, a spacecraft crossing the heliopause, sampling the boundary environment. Signals arriving from deep space, some repeating, some puzzling, some now useful as probes. A telescope staring into the early universe, revealing structure, complexity, and tension in models. The natural next step is gravity in its most extreme form. Because behind the formation of galaxies, behind the growth of cosmic structure, behind the engines that power quasars, there is a force that shapes everything, gravity. And there is no known gravitational environment more extreme than the region around a black hole. In this episode, Webb is not presented as a final answer. It is presented as a new set of eyes that extends the reach of observation. And there is a quiet philosophical implication that can be stated without drama. The universe was always this complex. The difference is that the ability to see it clearly is increasing. What changes is not the cosmos. What changes is the map, the deep field images, the exoplanet spectra, the dust-penetrating views into star nurseries. These are not just scientific results. They are evidence that the human ability to interpret light is expanding into regimes that were inaccessible before. And when access expands, mystery often moves. Some mysteries dissolve into understanding, others become sharper. The early universe, once described in broad strokes, is now becoming a landscape with terrain. This landscape includes unexpectedly bright galaxies, complex structures, and questions about rapid formation and growth. It includes atmospheres of distant worlds, revealing chemistry in places that can never be visited directly with current technology. It includes hidden star formation, uncovered by infrared vision. So in this episode, the mind-blowing idea is not a single discovery. It is a shift in the boundary of perception. Humanity can now observe parts of cosmic history that were once effectively invisible. This is why Webb matters, but Webb also sets up the final episode in a calm and natural way. If Webb reveals that galaxies formed early and evolved quickly, then the engines at their centers, supermassive black holes, become impossible to ignore. If Webb measures ancient light that has traveled for billions of years, then it forces attention toward regions where light can be trapped. If Webb expands the map of cosmic history, then it points toward the places where the map's rules become extreme. In the next episode, the focus will shift from the early universe's crowded structure to the objects that represent the edge of physical intuition. Black holes are often described in dramatic terms, but they do not require dramatization to be strange. They involve a boundary, the event horizon, beyond which signals cannot return. They involve time behaving differently in strong gravitational fields. They raise deep questions about information and the compatibility of fundamental theories. So in the next episode, the season will arrive at the place where signals and light meet their limit, not because the universe becomes supernatural, but because the physics becomes intense. In this episode, Webb has served as a bridge, from listening for signals to seeing ancient light, from fleeting bursts to deep time, from isolated phenomena to cosmic structure. The universe, when observed clearly, becomes more detailed, more crowded, and more alive with processes. And in that detailed universe, black holes are not anomalies. They are part of the architecture. In this episode, the telescope's job is to reveal what is there. In the next episode, the story will examine what happens when what is there becomes so extreme that even the concept of there changes. The eye has opened, the past has become visible, and the season's final threshold is approaching.